So today we're going to talk about types of nuclear decay equations and how to write nuclear decay equations. You are going to need your reference tables. We are going to be using tables O and table N. The first type of decay that we're going to talk about is beta decay. You can find the particle symbol on this note page, but you can also find it on reference table O. And you can find on table N the different nuclides that undergo beta decay there, and that's what we're going to be writing beta decay equations for, those nuclides. So for beta decay, any atom that falls above the band of stability or the belt of stability have too many neutrons, and they're going to undergo beta decay to release some of those neutrons, because that's going to make their neutron to proton ratio closer to 1:1, which makes them more stable. When they have too many neutrons, they're further from that 1:1 ratio, which makes them radioactive. So what happens is a beta particle, which is similar to an electron, is created when a neutron decays. So let's look at some examples. The first example that we have is for carbon-14. So if you look on table N, you're going to see carbon-14 there, and you're going to see that it undergoes beta decay. So hopefully everybody is looking at their reference table N, finds carbon-14, and under decay mode, you see it says B- minus for beta. Now, when we write a beta decay equation, you'll write the nuclide on the left-hand side, and then you draw your arrow. To the right of your arrow, I usually write the beta particle first. So it'd be 0, -1 with an E or a B for beta. Then you subtract across. So 14 minus the 0 on top gives you a 14 on top. And then on bottom, 6 minus a -1. You always subtract across an arrow. A 6 minus a -1 gives you 7, because it really turns into 6 plus 1, because the two negatives turn into a positive. And that's how you get the nitrogen, because you look up that 7, which is the atomic number on your periodic table. It's the atomic number for nitrogen, okay? For rubidium, you can do the same thing. So if it asks you in a question to write the decay equation for rubidium-87, okay? Now, this one's not on table N, so what they would have to tell you is that it undergoes beta decay. So you know that you're going to have to write this on the right-hand side. So again, subtract across. 87 minus, remember this is like subtract across. Minus 0 is 87. 37 minus a -1 is really adding a 1, and you get 38. That's beta decay in a nutshell. Now, for writing decay equations, there's going to be a whole guided worksheet that is attached to this lesson that you can go to if you're not really following what I'm doing in the lesson, okay? There's a picture to the right that shows beta decay. It releases a beta particle, which is really just a fast-moving electron. Sometimes gamma rays can be released as well. This is another example of a beta decay equation. So if you looked up thorium-234, it undergoes beta decay, which you can see from table N. You're going to see under decay mode B minus. Okay, now when we say that mass and charge must be conserved, the total mass on the left must equal the total mass on the right. Okay, and when you have mass, that's going to be the top number. And the total charge on the left must equal the total charge on the right. That's going to be the bottom number. Okay, so this is mass, and this is charge. Charge really just is atomic number. Okay, so if we take the left side, the total of the top, the sum, is 234, and on the right, 234 plus 0, the total is 234. And on the bottom, on the left-hand side, it's 90. On the right, 91 plus -1 is 90. Okay, so those are going to be your totals. So the left and the right have to equal 234 on top and 90 on bottom. And if you don't get that left and right to be equal, you did something wrong. So this is kind of a good way to check your work. So on this slide, it wants you to try your own example of a decay equation for beta decay. And it says construct the nuclear decay equation for carbon-14. Now, we just did that on the previous slide, which I didn't catch. So we're actually just going to try it instead. Let's just do gold because it also undergoes beta decay. So instead, we'll change this to gold 198. Okay, and it says remember that the mass and charge must be conserved. That means that the sum of the top on the left must equal the sum of the top on the right. Okay, and the sum of the bottom on the left must equal the sum of the bottom on the right. Okay, the top is the mass and the bottom is the charge. Okay, so let's try that. Take a minute and try to write the nuclear decay equation. Now, beta decay specifically because we know the decay mode here for gold 198. Okay, so the example that I gave you here was for carbon-14, right? Which obviously I did the example 2 slides ago. So I changed it to gold 198. So I'm going to do this with you, okay? So we have 198 on top. AU is the symbol. Now, how do we find the bottom number? That's where you have to go to your periodic table. You have to fill that in yourself. So you look up AU and you see that its atomic number is 79. You draw your arrow. You draw your beta particle, 0, -1, with the beta sign or with the E. You can draw it either way. Honestly, I always draw the E because for some people, they don't like to draw the B, but that's how you draw it if you want to. Okay, now you subtract across. 198 minus 0 is 198. 79 minus a -1 is actually 80 because you're really double negative, you're adding. You go to your periodic table, you look up what atomic number 80 is, and it's Hg, which is mercury. And that is all you have to do. So that's your decay of gold 198. So here you're going to check your understanding. Can you identify the type of nuclear decay mode from table N? Can you construct a beta decay equation? If not, time to go back and rewatch those parts. Now we're going to take a look at another type of decay. It's positron decay. They really do call it positron emission. They don't really refer to it too much as decay. So when you have an atom that is below the band of stability or that belt of stability, that means they have too many protons. And what they're going to do is they're going to release a positron because a positron ends up reducing the proton number by 1 because you have that +1 on the atomic number or charge spot. So it's going to reduce the proton count by 1. So the positron is really just the opposite of a beta particle. It's a positive electron. So that's really all it is. And if you look on table O, it's 0 over +1 B or 0 +1 E. Okay, so when you have an unstable nucleus, the proton's going to decay to a neutron and a positron's going to be emitted. So if we took a look at K37 or potassium-37, if you go to table N, you're going to see that not many nuclides undergo positron emission, but there are a few. So potassium-37 is one of them, neon's another one, calcium is a third, iron's a fourth. So those are really the only 4 things on your table that undergo positron emission. So let's take a look at potassium-37. Remember, the total of the left has to equal the total of the right. So we had potassium-37. You're going to write your positron particle, okay? And then you're going to subtract across. 37 minus 0 is 37. 19 minus 1 is 18. You look up atomic number 18, and you get that it's argon. Your totals of the left have to equal the totals of the right. So if we look at our totals, it's 37 on top, 19 on bottom. 18 plus 1 is 19, so we are good there. 37 plus 0 is 37, so we are good there. Okay, so your totals are equal. Now let's try our own, okay? Let's try it for calcium-37. We see that it undergoes beta plus. Beta plus, again, is positron. All right, so try your own, and then remember, mass and charge must be conserved. On the next slide, you can check your work. Here is the answer to that calcium-37 positron emission, and I'm going to show you the steps. You would write your calcium-37. Now, the 20, okay, is the atomic number for calcium. That you'd have to get from the periodic table. That is the atomic number. That bolded number from the periodic table. Okay? Then you draw your arrow. This is all like added information, not part of the equation. Okay. Draw your arrow right away. You draw your positron particle. Then you subtract across. 37 minus 0 is 37. 20 minus 1 is 19. Look up atomic number 19, and you're going to see that it's potassium. You're looking this up also on the periodic table. It's the atomic number of potassium. And then you're done. Check your understanding again. Can you identify nuclear decay mode from table N? Can you do positron decay or emission? And if not, you're going back and you're rewatching parts of this video. One of the more popular types of decay is alpha decay. Any atom with atomic number 82 or above, so 82 or more protons, that's really what that's saying. Is likely going to undergo alpha decay because it's huge and it's got too many protons and too many neutrons. Alpha particles are very weak due to their mass being so large, and an alpha particle is the same as the helium nuclei. So if we were to draw our alpha particle, it could look like the helium nucleus because it has the same number of protons and neutrons, or we can draw it as the alpha symbol, which that's a little too wild there. Okay, it's just like a weird looking A. So when you have one of these large atoms, it has 82 or more protons, so atomic number 82 or above. It's going to be radioactive because it has too many protons, too many neutrons, so it's going to have a large and unstable nucleus because that neutron to proton ratio is going to be far from 1 to 1. And what you want to happen is you want it to become a small, more stable nucleus, and it does so by releasing an alpha particle. So what we're going to do on the next slide is look at some alpha decay equations. So if you look up uranium-238, you're going to see on table N that it undergoes alpha decay, okay? And if you looked on the periodic table and saw that its atomic number was 92, that is above 82, so you would know it undergoes alpha decay. Again, mass and charge must be conserved, so the total mass on the left has to equal the total mass on the right, and the total charge on the left has to equal the total charge on the right. And in the paragraph on the left, it tells you those totals. I just circled them. So this is going to be the same as the other types of decay where you just subtract across. You have uranium-238, 238's number on top. You're going to subtract the 4 from your alpha particle. That's your alpha particle I just circled. Again, when I write these out, I usually like to write this first. So 238 minus that 4 gives you 234. And then on the bottom, 92 minus 2 from the alpha particle gives you 90. Look up atomic number 90, and that's how you get TH. So now you're going to try your own for radium-226, okay? I already took the part of table N where you're going to find that it is alpha, all right? So you would write radium-226 goes on top, and your job is to find the atomic number and then finish your equation. Answer will be on the next page, and I'll take you through the steps. So you have your radium-226, atomic number is 88, that you had to find from your periodic table. And remember, that is the atomic number, okay? You subtract across, and it shows you this above. So it's like A, if this was A, right, it'd be A minus 4. So 226 minus 4 gives you 222. Then the bottom number would be Z minus 2 because you're subtracting these here. 88 minus 2 is 86. And you're going to look up what atomic number 86 is, and it's Rn radon. So then you write the symbol there. So again, we come to a check our understanding. Can you identify the type of nuclear decay mode from table N? And can you construct nuclear equations for alpha decay? If not, go back to the beginning of alpha decay, watch that part of the video again to try to better your understanding. The last type of decay, and I put decay in quotations because it's not really decay, is gamma decay. Gamma is the strongest type of radiation, and it just accompanies decay, but we're not going to write equations for it really because it's not a written nuclear decay. It's not written because it cannot change the mass or the charge of any of the species, because if you look at its notation, the top number and the bottom number are both 0. So the mass, again, is the top number, and the charge is the bottom number. So if those are both 0, it's not going to change anything about the nuclide that's undergoing this type of quote-unquote decay. It's really just going to emit this type of radiation, which again is a very strong type of radiation. So when we write decay equations with gamma, you really just write this particle next to whatever nuclide you're talking about because it's just emitting it. It's really a ray, and that's all you're doing. You just write that symbol, which is like a squiggly Y. I don't even write it well, okay? And then that's all you would write. And then you're done. And you write the symbol that you started with, you write the squiggly Y, and that would be your gamma decay. So in this slide, we're going to talk about the penetrating power of the 3 different types of radiation. The 3 types are going to be alpha, beta, and gamma. Now I'm switching up the colors here because we're going to talk about their relative strengths. So the strongest one is going to be the gamma ray. Gamma can get through, or actually can be stopped by, I should say, concrete. So it can get through paper, it can get through aluminum, but it can only be stopped by concrete. So if you've ever been to the dentist and they put that shield on you, okay, maybe like an aluminum vest, right? It's going to be some sort of metal vest that is put on you to protect your internal organs when you're getting an x-ray. Any x-ray you get, you usually wear some sort of vest, and that's to protect your internal organs from this type of radiation because it is very strong and it can damage and mutate your internal organs. So that's why you have that type of vest. Now, the same goes for beta because beta can be stopped. I'll be here. By aluminum, okay? So beta falls somewhere in the middle when you're comparing the 3. Now, when you have alpha, okay, that's going to be here. Alpha can be stopped by paper because alpha is the weakest. So when we're comparing the 3 from weak to strong, we have our weakest and then our strongest. So that's kind of like your scale of penetrating power of the 3 different types of radiation and what they can be stopped by, and you do need to know that. This is just another slide that recaps the penetrating power. The lowest is going to be the alpha, the highest or the strongest is going to be the gamma, and then the beta falls somewhere in the middle. It's important to also know that radiation is charged, and because it's charged, it can be separated into a magnetic field. If it's separated into a magnetic field, it's important to know what's going to be attracted to what. So the main thing here is to know that opposites attract. Now, just to break down the particles, we know that alpha is 4 over 2 He, gamma is 0, 0, Y, okay? So gamma has no charge. Alpha is very positive, okay? Beta is 0 over negative 1 E, so beta is negative. So when we're talking about what's going to go where in a magnetic field, the beta particle is obviously going to go towards the positive end of a magnetic field because opposites attract. A negative beta particle is going to go towards the positive end of a magnetic field. So hopefully that makes sense. We're going all based on this opposites attract. A gamma particle is going to go straight through because it has no charge. An alpha particle is going to go towards the negative end of a magnetic field because it's positive and opposites attract. So it's really just important to know that opposites attract as long as you know the charges of each of the particles. And then remember that gamma doesn't have a charge, so it'll go straight through. You're good to go. This is a very classic Regents multiple choice question. So now we're coming to the end of the lesson. So check your understanding. Can you determine the penetrating power of each emission type? And I'm just going to add in, can you identify what's going to go where if each type of radiation were to be separated into a magnetic field? So from this lesson, you should be able to differentiate between artificial and natural transmutation, which we kind of did in lesson 1, but it should still carry into lesson 2. Okay, natural transmutation happens on its own. Just to recap, and this must be forced to happen. We're actually going to take a look at this more in the next lesson. You really just need to know natural. Everything that we have looked at today has been natural. Okay, so natural is alpha, beta, gamma, positron. So you really don't have to know any of the artificials yet because that is fission fusion, which we're doing in the next lesson. This was just a little bit of an intro, I guess. Identify the type of nuclear decay mode. That is mostly going to come from table N. Construct nuclear equations for alpha, beta, and positron decay. So we need to know how to do that. Table O, table N are going to help you with that. And then determine the penetrating power of each emission. And then again, how it would separate in a magnetic field. Okay, so that's been today's lesson. Hopefully you got something out of it, and I'll see you in the next lesson. And please make sure you take a look at the guided practice for decay equations, because the ones that I showed you today just brush the surface, but they do get more difficult. And when you try to attempt the worksheet, you're going to be confused if you don't look at that. All right? And again, see you in the next lesson.